Okay, continuity, section 2.3, continuous functions, again, is a topic that you were introduced to back in pre-calc. What is continuity? What does it mean to be a continuous function? It is a function, it is continuous at a point if the limit at that point exists and it also equals the function value. So remember what it means for the limit to exist. As we approach it from the left and as we approach it from the right, we get the same answer, right? That would make my limit exist. And it's also saying then that the function value has to match that as well. So as long as all of those things come together, it's continuous at that point. A function is considered a continuous function if it is continuous on its entire domain. So this happens for every single point on the domain. There are actually 4 types of discontinuities. We will focus on 3 of them. So I'm going to show you this next page. I would pause. I'm going to give you a better page to write down than this one, but this just kind of overviews the 4 different types of discontinuities. We have a removable discontinuity, which is a hole in our graph. That comes from something simplifying out of our rational expression. We have a jump discontinuity, comes from either a step, which would be like our greatest integer function, or a piecewise. We have an infinite discontinuity, which comes from a vertical asymptote, would look something like this. And the last one, this is the first and last time you're going to hear me talk about this one, and that is an oscillating discontinuity. That comes from a function such as sine of 1 over x. It exists. That's about the last time it's going to show up here for us. Okay, so the 3 that we focus on would be then the removable, jump, and infinite. And what I really want to make sure that we have down is identifying it and justifying it. Okay, so good notes on this page. Remember, an infinite discontinuity is going to come from an asymptote, specifically a vertical asymptote. So remember, we talked about vertical asymptotes before when we head towards an infinity in our limit as x approaches some number. So let's give ourselves a picture of an example of an infinite discontinuity. Would be something that approaches an asymptote, right? So we might have something that looks like this. So you guys are going to be asked to identify and justify these discontinuities. So how do I identify it? Well, I use the specific word. So like we would identify this as an infinite discontinuity. And you have to say where. So it is at wherever that asymptote is going. So this is an infinite discontinuity, and I have mine drawn at x equals 2. So we would say at x equals 2. You say the x value where that discontinuity is happening. Your justification, when it is an infinite discontinuity, your justification is going to be either a right-hand limit or a left-hand limit that is headed towards an infinity. Okay, and I'm going to put both up here. You technically would only have to have one of those as your support or your justification. So the limit as x approaches 2 from the left of f of x was headed towards negative infinity. The limit as x approaches 2 from the right of our function was headed towards positive infinity. So generically speaking, for my notes purposes, for my justification is either my right or left-hand limit is going to equal an infinity. Right and or left-hand limit, it doesn't matter which one, or both, is going to equal either positive or negative infinity. That's the justification needed to distinguish it as an infinite discontinuity compared to either of the other 2 options. My removable discontinuity. In a removable discontinuity, I am going to have a hole in the graph. That hole can be accompanied with a value somewhere else in the picture, or it doesn't have to. So it could look like this. It could also look like that. Either of those would be considered a removable discontinuity. So again, removable discontinuity, I again identify where it's happening. So like in this picture, I have it happening at x equals 1. My justification has to be this, that the limit exists at that x value. So we do have a limit of our function as x approaches 1. And let's say it's 2. Okay, so the limit exists, and notice it is not a right or left-handed one. It is a limit, meaning both sides head to the same place. But I also have to show that the function value does not match that. So f of 1 equals -2. Now I do want to give a second option on this one. What if I eliminated that dot? What if that dot just didn't exist? Would this still be a removable discontinuity? It would. And all that would change is that this would then say like undefined or does not exist. Okay? Either of those are fine because still my function value does not match my limit. The limit exists, the function value does not match it. Okay? And so that's exactly what you need to show as your justification. That the limit does not equal the function value. And we'll say as x approaches our number and the function at that number. Limit exists, doesn't equal the function value. The jump discontinuity. Jump discontinuity is going to look like some sort of a piecewise function or step function. So maybe it looks like this. Okay. So on that one, you can see that we would have a jump discontinuity. It jumps from one piece of the graph to the next piece of the graph and this one's happening at x equals 0. Okay, so again, I use the discontinuity title, infinite, removable, or jump, what x value it's happening at, and my justification. My justification for a jump discontinuity is that the left-hand limit is not the same as the right-hand limit. So the limit as our function approaches 0 from the left comes up to 0, and the limit as our function approaches 0 from the right is 2. And notice my left-hand limit and my right-hand limit do not match. So again, in general speaking, I would say the limit as we approach our number from the left does not equal the limit as we approach our number from the right. So the stuff at the bottom in green is basically just kind of your notes as to what is the generic thing I need to be saying to justify that particular type of discontinuity. What is it that distinguishes it from another type of discontinuity? Now, while you guys are still writing, let me just throw this out there. I did have somebody say, well, can I just say that the limit at 0 does not exist? Is that enough to say that it is? Isn't that true? Isn't the limit here does not exist at 0? Is that enough to distinguish it as a jump discontinuity? It's not, because wouldn't this limit also not exist, right? So that would not be enough to distinguish it from an infinite discontinuity. So we just have to be careful that kind of fine-tuning what actually distinguishes it from the other types. Any questions for me on that? All right. So this next part, you guys, you really don't need to write this down. But there's just kind of generically speaking, things that are always continuous would be like polynomials. So like x squared plus 3x plus 7. Always continuous. No domain restrictions. Think about things that don't have domain restrictions. Absolute value functions. Y equals the absolute value of x. Always continuous. Some things that are continuous only on their domain or may not be continuous from negative infinity to infinity would be things like rational expressions, exponential, logarithmic, trigonometric, and radicals. So we'll look at, okay, yeah, I can say it's continuous on its domain, but maybe not everywhere. So we kind of have to clarify where things are continuous if it's something like a radical expression. All right, so on this one, find the points of discontinuity for the function, identify the type of discontinuity, and give a justification for your answer. As we are identifying the type and giving the justification, I want you guys to consult your calculators. So as soon as you get this down on your paper, and you kind of decide on what type of discontinuity. I want us to look at our graph here so that we can speed things up a little bit as far as our justification on which type we think it is. So if I grab my calculator here, let's go. All right. So looking at this, first of all, I did not have to look at the picture to answer the first type, what type of discontinuity and what are the points. And that comes from what I know about a fraction. And I know a fraction is going to have domain restrictions or discontinuities from our denominator. So I know that where the denominator equals 0 is going to be a discontinuity. Add 5, divide by 2 at 5 halves or 2 1/2. I know there's a discontinuity. Which type? Well, it didn't cross off with anything in there, so it's not a removable. It's not a hole in my graph. That's an asymptote, right? So, and as I look at the picture, it 100% supports that. I've got an asymptote running right here at 2 1/2. Okay? So then I would identify it, if I go back to my 3 options, as an infinite discontinuity. So we would start out with infinite discontinuity at x equals 5 halves. And then my justification is I would look at that picture, and my justification for infinite discontinuities is the right-hand limit or the left-hand limit or both are headed towards an infinity. So the limit as f of x of x as x approaches 5 halves. And let's go from the left. If I go from the left, that'd be this piece of graph is headed down towards negative infinity. One of those is actually enough, but I'm going to put both right and left up here as x approaches 5 halves. From the right is infinity. And infinity is an infinite discontinuity. Any questions on that? Okay, this next one we need to talk about a little bit here. Notice on this one I'm not asking you to justify, and there's a reason for that. It says find the points of discontinuity for the function, identify the type of discontinuity. We need to go back to what is the domain restriction on a radical? Well, a radical has to be a positive number, right? So if I'm looking at a square root, I know what's underneath my square root has to turn out to be a positive number, or x plus 4 has to be greater than or equal to 0. So in this one, x has to be greater than or equal to negative 4. And basically what we can say is this is continuous on its domain. Once we get to that domain, if I were to have, you got your calculators in front of you, if you were to grab your calculator and graph that, it would look something like that direction, something like that. And once I get onto the graph, it's going to be continuous forever. Is that I'm never going to have to pick up my pencil, there's graph from there on out. But only once I get onto the graph. So it is continuous on its domain. Okay. Where is it discontinuous? Because it says find the points of discontinuity. It would be discontinuous for anything that is less than negative 4, right? So just answering the question up there, it is discontinuous for all x less than negative 4. Technically an infinite discontinuity, but we would not have a justification for that. Questions on that? All right, let's look at another one here. Find the points of discontinuity for the function. Identify the type of discontinuity. Give your justification for your answer. If this one is not one you are comfortable with, I would grab my calculator and look at the picture of it. So let's go ahead and again, this is kind of what I was wanting us to graph earlier anyway with our absolute value. So let's all make sure we remember where our absolute value is on our calculator. Grab your calculator and make sure you can graph that. And we actually talked about this one a couple days ago, so hopefully you remember, because it's really hard to see on our calculators. But is there a discontinuity in this graph? Yes, it's happening at what? 0. Which type? What of our three types are we looking at? Are we looking at an infinite, a removable, or a jump? Jump. We are looking at a jump discontinuity. So we would say jump at x equals 0. And our justification, remember for justification for a jump discontinuity is two limits. A left-hand limit does not equal a right-hand limit. And we would have to just show those two. The limit of our function as x approaches 0 from the left looks like -2. And the limit as our function approaches 0 from the right is +2. That's my justification. Questions on that? Yes? Infinite, you would just need one. You'll see I always will write both, but you would technically, one of those is enough because one of those gives you a vertical asymptote, which would be an infinite. Yep. Yeah, on this one and on removable, you have to have two things listed though. Otherwise, it's not enough. All right. Last little part here is kind of getting that same conversation going, but from a picture. So it says use the picture of our function f of x to answer the following. I'll give you guys a minute to look at that. Your questions are, is it continuous? What's the limit as we approach 1 from the right? Is it continuous at specifically 1? Because these can be different answers. Is it continuous and is it continuous at a specific point can be two different answers. Okay, so give you a second to look through those, discuss as your table, come up with my 4 questions there. Last question for those that can't see it in the back is f defined at 1. All right, the first one's pretty easy. Is f continuous? No. Another way of asking that is, can I trace the whole thing without picking up my pencil? No. And if I say no to that, it's not continuous. Continuous, I can trace the whole thing without picking up my pencil. So no, not continuous. What about our limit as we approach 1 from the right? 2. Here's 1, approach from the right, we are headed up to 2. Okay, is it continuous at 1? No. Which type of discontinuity are we looking at there? Jump. So no, it is not continuous at 1. We are looking at a jump discontinuity. If I wanted to justify that, again, justification, since this is new to us today, justification for jump discontinuity is that the limit of our function from the left does not equal the limit of our function from the right. Okay, so not the same. It's a jump discontinuity. Is it defined at 1? What do you think? Yes or no? No. It is not. We don't have a, oh yes it is. Keep looking. Right here. It is defined at 1. Close dot. F of 1 is -2. Questions? All right. Last one. You drawing your own. Now, some of us had a lot of trouble drawing that first one. So make sure you and your table partners have the same looking graph, especially for that first piece of it, 2 minus x. And then answer your questions once you got a graph drawn. What time do we get out of here? May have run over last time. We got time. We're good. If you are stuck on the graphing part, guys, when all else fails, plug in points and see what you get. Where is the graph at x equals 2? Where is the graph at x equals 0? Where is the graph at x equals 1? Plug in points and see what you get. We all kind of have our own methods for graphing piecewise. I'm going to go ahead and get this graph because we're going to run out of time here pretty soon. But remember, guys, this equation, y equals 2 minus x, is just y equals mx plus b, not in standard form. So it really is y equals negative x plus 2, right? Y-intercept up at 2, slope of -1. We know how to graph that. And open dot here at 1. Okay, graph should look something like that. There's your 3 pieces. Graph the function as part A, find any points of discontinuity. We have a discontinuity happening at x equals 1. Our type of discontinuity, what would you call that one? Removable. A removable discontinuity at x equals 1. The limit and the function value don't match. Tell if they're, oh, I guess I answered the next question. Removable. And is this a continuous function? No, not if we have a discontinuity. All right, your assignment, page 84, you are doing 1 through 23 odd.